Here's an AC power adapter that you might plug into a wall to power a small electronic device. This particular one takes in 120 volts AC and outputs 9 volts DC. Let's remove the cover and see what's on the inside. We have transformer, capacitor, and several diodes. The transformer has a primary coil behind this yellow tape. Here's the secondary coil. It outputs a much lower voltage, around 9 volts, but it's still AC. The purpose of the diodes here is to convert the AC into DC, but it's a pulsating DC, and this capacitor here is the smoothing capacitor. Here's the basic circuitry of an AC adapter laid out using light-emitting diodes so we can see it in operation. There's 120 volts AC cord to a transformer. The transformer is going into a diamond-shaped configuration of diodes, here made with light-emitting diodes. And the output from that is powering a regular, small, incandescent light bulb.
Now let's look at the schematic diagram so we can understand how this works. We have an input here, which is typically 120 volts AC on the primary coil of the transformer. Here is the secondary coil of the transformer. AC means that the two wires are alternately switching from positive to negative and negative to positive. Here it is switching a few times so you get the idea. Remember that a diode, and here's the symbol for a diode, allows current to only flow in one direction. So that's the flow of the current. If this end is positive and that end is negative, current will flow. But if you try to make this end positive and that end negative, you will get no current. So, coming back up here to our transformer, the output is AC. At this particular moment, this wire is positive, this wire is negative. And so when the positive voltage over here will cause this diode to be turned on, and therefore the plus positive voltage comes out over here. The negative wire of the transformer is connected to these two diodes, but this one is going to be off. This one will be on. And so it's like a closed switch. So the negative voltage will then appear there. So these two diodes are on, and the other two diodes are off. Now, a fraction of a second later, the polarity of the two wires will be reversed because it's AC. This top wire is now negative. We have negative on the back end of this diode, so that one will be off. But this one will be on. The other wire of the secondary coil of the transformer is positive. It's connected to these two diodes here, and therefore this one will be on because it's positive on the back end of the diode, and this one will be off. So the positive voltage ends up coming out here, and the negative is connected here. So regardless of which wire is positive or negative, we always have positive coming out here, negative coming out there. And so that is what direct current is. One wire is positive, the other is negative, and they do not switch back and forth like AC does. So let's look at what our voltage graphs look like at two different places in our circuit. Here at the output of our transformer, the graph of voltage as a function of time is going to look like this. AC. But here, the output of our rectifier bridge, the voltage graph is going to look like this. One way we can think of what the rectifier bridge is doing is that every time the voltage tries to go negative, effectively the rectifier bridge is simply switching the wires. So when we have this and it tries to go negative right at this point, it just switches the wires and we get another peak, positive voltage. Now our last thing we need to talk about here is the smoothing capacitor. We don't want our voltage graph to look like this. This is, although one wire is always positive, the other wire is always negative, it's a pulsating DC. The voltage goes from around 0 up to some maximum and back down to 0. Then back up to some maximum, back down to 0. What we want is a graph instead that looks like this. A constant voltage, just like you would get from a battery. And that's what the smoothing capacitor does. You can kind of think of the smoothing capacitor like a sponge. When the voltage is high, like it is here or here or here, then it soaks up that extra charge, that extra current. When the voltage is low, like here or here or here, then it releases that excess charge onto the wires. And so that you end up with a constant or nearly constant voltage and a nearly constant current.
The diodes of the rectifier bridge are turning on and off in pairs on opposite sides of the diamond. Here, this is regular 60 Hz AC, and you can't see the blinking with your naked eye. However, if I use a signal generator to provide AC to the bridge with a different frequency, you can actually see what's happening. Here is 6 Hz, and here is 0.6 Hz. Here's the oscilloscope set up to look at the voltages in our circuit. There's the probe with some alligator wires. Right now we are just looking at the output of the transformer. The output of the transformer, which is AC 60 Hz. Now I've moved the probes of the oscilloscope to the output of the bridge rectifier. And here is the oscilloscope trace.
Notice that the voltages are all positive. They're above that midline on the oscilloscope, but it's a pulsating DC, rising and falling, rising and falling.
Now I'm going to add a smoothing capacitor to the circuit. This is a 1000 microfarad capacitor, and I'm going to use the clips for the oscilloscope to clip on also to the output of the rectifier. Now we've got a good connection, and let's look at the oscilloscope trace.
You can see that the voltage, while not perfect, is nearly constant, and that's what we wanted.